Welcome to homework.
All right. We have got an acid chloride. It's an alpha beta unsaturated acid chloride, but it's an acid chloride nonetheless. And we've got this amine, which has what? A 1, 2, 3, 4 carbon chain. So instead of drawing all those carbons, I'm just going to call this H2 nitrogen and then N-bu. Stands for N-butyl, which means a straight butane chain. Okay, just be a little simpler to draw, but it just means it's the same as 1, 2, 3, 4, right? So this is N-butyl. Okay, just wanted to point that out. Okay, so what kind of reactivity do acid chlorides have? Well, we know that they react with any sort of nucleophile, such as, for example, an amine or an alcohol, to form esters, right? So consider that this acid chloride is in resonance with the following. And also don't be thrown off by this alpha beta unsaturated part. When you have an acid chloride, the almost no matter what nucleophile you have, the carbonyl carbon is going to be far more reactive than the beta carbon. So just keep that in mind. All right. So that's the resonance structure we're interested in, right? And it shows us that the carbonyl carbon is very electrophilic, which means that's a perfect spot for our nucleophile to attack. So let me just move this down here, and we'll scroll down and continue on. Okay. So this nucleophile will attack, and we'll get our tetrahedral intermediate, as it's called. Tetrahedral because all of a sudden this will have 4 bonds. We've got our chlorine, we've got O minus, and we've got our nitrogen, which has a proton, another proton, and it's N-butyl group. And we've still got the unsaturated bit here. Great. Okay. I'll also point out that it's not necessary to draw this resonance structure. We could have drawn instead, I'll just draw this off to the side in case you don't have space for it in your online homework program. You could have also drawn this just attacking the carbonyl directly without first forming the carbocation. So this is also a valid mechanism. That could have been the first step leading to that. Okay. Next step, we are going to do some proton transfers. I forgot to draw the positive charge here, got sidetracked. Okay. And we're basically just going to transfer a proton from the oxygen, or from the nitrogen onto the oxygen. Sometimes this is shown happening with another molecule. Like if we were doing this in water, we might first show water deprotonating the nitrogen, and then in a separate step, we would show hydronium come in and protonate the alkoxide. But if you're on limited space, which maybe you are with your online homework program, we're just going to show this proton transfer step directly. And I left behind an old arrow from that other example. Okay. Chlorine. Now we have OH. have our nitrogen, which has a single proton, and our N-butyl. Okay, and then we're going to lose chlorine from this. This is a good leaving group, and this lone pair on oxygen wants to push down and reform the carbonyl. All right. So we lose our tetrahedral intermediate because we've lost chlorine, and we form essentially what is a protonated amide. And we've still got Cl minus. And as final step, we can show the deprotonation of the oxygen from Cl minus. Or if we had had another solvent present, if we were doing this in some, water or something, we would show water doing this as opposed to chlorine deprotonating it. Chlorine, as we know, is a rather weak base, or chloride ion is a rather weak base. So it's kind of unlikely that it would actually be chlorine doing the deprotonation, but when we don't have any solvent, we're forced to use the counter ions to do the charge balancing steps. Okay. And now for this final product, I'll show the actual N-butyl 1, 2, 3, 4. And that's our final product.